Hi, my name is Oluwaseun Martins, and in this video, we'll be looking at the use of sensors and vision systems in robotics. So, like we know, robots are AI systems, and by that, they act in a way that is similar to human beings. So, for a robot to perform excellently in whatever application it has been deployed, the robot needs to find a way to know what is happening around itself, and also to know the state of which its own internal operations are. Like humans, we can sense when our environment is hot or cold or warm, and at the same time, we can sense when we are hungry and when we are thirsty. So, in the same vein, for a robot system to perform excellently in whatever application it has been deployed, the robot needs to find a way to measure the physical quantities around itself externally, and also to be able to evaluate its own state internally. For instance, the battery level is an external state of the robot. It needs to know what battery level it is. Maybe it needs to be recharged, or maybe whatever it is. So to make that possible, that is where sensors and vision systems come to play in robotic systems. So what sensors, what they do is to measure physical quantities and convert them into a readily manipulatable electrical signals, and in most cases voltage or current signals, so that those signals can now be used as the state of whatever physical quantity that sensor has measured in a sense. And so what happens in sensors is that there's what we call the transducer in sensors. So what the transducer, what it does is to convert the physical quantity into the electrical signal. So what transducers, what they do in sensors is to convert the physical quantity, maybe temperature, maybe pressure, maybe stress, maybe force, maybe flow, into a corresponding and usually proportional change in an electrical quantity. So what we're saying is that whatever change it is in the physical quantity that a sensor is measuring, the electrical signal that the sensor should give should be corresponding and proportional to the change that the physical quantity is experiencing. So, and the electrical signal, like I said earlier, is basically a voltage signal or current, but in most cases they are voltage signals. But before any readout from a sensor can be used, there are some other manipulations that are being done before the electrical outputs of that sensor can be available for use. There's some other conversions that you might do. For instance, if you have worked with ultrasonic sensors before, you need to convert whatever reading that you're getting from the ultrasonic sensor into distance. By itself, ultrasonic will not give you distance as an output, but you need to convert the pulse that you're getting back into the corresponding distance measurement that you want to know from that ultrasonic sensor. So that's what we're talking about, that the output from sensors are not directly usable. Some other manipulations are done before the electrical output can be available for use. So robot itself, for it to perform excellently in an environment, it needs to be able to measure the physical quantities of its own environment and also its own internal state. And there is always a controller. Like in the human body, we have the brain. So for the robot system, there's always a controller that would handle all the information from these sensors based on the programming that has been done on the controller. So the controller can be maybe your ESP32, can be your Raspberry Pi, can be your Arduino, or can be a combination of any of these, depending on the level of complexity of such robots. So sensors generally makes a robot aware of its environment. So there is no way you can develop a robot without sensors or maybe vision systems, because even the tasks the robot needs to conduct in the environment, the robot also needs to sense that it's actually doing that task or not. So sensors are very important. Now, the major merit of using sensors in robotic systems is that any robot that can perceive its environment, such robots are easier to train and also deploy to perform complex tasks, in the environment, and are also adaptable to a wide range of applications. So listed here are just some common sensors that you find in robotics, like the tactile sensors, the close range proximity sensors, the angular position sensor, infrared sensors. Also, you have probably your sonar sensors, your laser, your radar, your compass and gyroscope, because your robot works in 2D or 3D space, depending on the kind of complexity your robot is working with. So you might need a compass or a gyroscope to get those coordinates. Also, force is another sensor that you might want to use, particularly if you have a robot arm that needs to grip something. You need to be able to measure the force at which is holding that particular component, so that it doesn't deform under the grasp of that robot. Also, the GPS, that is the global positioning system, that you might want to also use to know the coordinates or the location of your robot. Also, the vision sensors also is another kind of sensor that you might want to use, maybe a camera in this case, so that your robot can actually make some decisions based on information gathered from an image through the use of cameras. So sensors are generally classified into we have the general classification of sensors, and we have the other classification, which is also specifically classified as shown. So for the general sensor classification, you have the active or passive sensors, and also you have the contact or the non-contact kind of sensors under the general classification. So a sensor can either be active or passive, or contact or non-contact sensor. So there's also the specific classification of sensors, either proprioceptive sensors or the exteroceptive sensors. So for the active, so these are sensors that actually emit energy in the environment. For instance, your ultrasonic sensor, emits energy into the environment, because for ultrasonic you have the transmitter and the receiver. So it actually sends out some signal into the environment, and the receiver waits until that signal is being reflected back to it. So those are active sensors. Also, you have the infrared, because when you put an infrared sensor into use, the infrared laser would be on. So at any time that laser is intercepted, then the sensor can actually measure the distance at that point. So those are active sensors. Those are sensors that actually emit energy into the environment. Then also you have the passive. So passive sensors are sensors that do not emit any energy to the environment. For instance, a camera is a sensor, a vision sensor, and it does not emit any energy into the environment, but it actually waits until it receives information from the environment. So that's an example of a passive sensor in that case. Then for the contact and the non-contact sensor, so you have the force or torque sensors. So those sensors, they need to have contact before they can actually measure the force or the torque, that's been exerted at that point. So those are contact kind of sensors that they need to make contact with the environment before they can actually measure whatever it is that they need to measure. And we have the non-contact sensors. Those are like the range sensor or the proximity sensor. If you have the passive IR sensor, the one that is being used to sense the presence of human beings, you don't need to touch it before it can actually sense the presence of an human being. So that's a passive IR sensor in that case. Then for the specific classification, we have the proprioceptive sensors. So those ones measure the internal state of the robot itself. Like I said earlier, like humans, we need to know our state internally. When we are hungry, we know. When we are thirsty, we know. Those are instances whereby we sense our inner state, and also you can sense our external state as well. So for the internal state for robot, under the specific classification, you have the proprioceptive, that is for internal state measurements for the robot itself. So like the battery level, the wheel position, or the joint angle of your robot arm, they are being measured by proprioceptive sensors. Those are the sensors that measure the internal state of the robot. Then you have the exteroceptive, that is for external state. So sensors like cameras, like laser scanners, like force sensors, like torque sensors, like proximity sensors, those are exteroceptive. Those are sensors that measures physical quantity from the external, from the surrounding of the robot. Those are exteroceptive sensors. So when purchasing a certain sensor, there are some technical information that you need to check about that sensor to know if that sensor is appropriate for the work you intended to apply to. So, and those technical informations are called sensor characteristics. So what they tell you about the sensor is they tell you about the capability of that very sensor. For instance, if you want to buy a camera, what you might be interested in is to know what is the frames per second of that very camera. The higher the frames per second of that camera, the higher the streams of images that camera can capture in a second. So depending on the kind of work you want to apply that sensor to, will tell you how many frames per second kind of camera would you be going for. So that is just one of the ways by which you need to be very diligent in checking the technical information about any sensor you want to buy, if they actually match your requirements. So I've listed here, we listed 9 here. Number 1 is the dynamic range. So dynamic range just tell you the ratio between the lower and the upper limits of that sensor, usually in some cases in decibel. So what we are saying is this: for instance, let me say you want to measure a distance, using a certain proximity sensor, or you want to measure the temperature of a certain entity using the temperature sensor. Now you need to know what is the temperature of what I want to measure, what is the possible maximum temperature that entity can attain. If that entity, for instance, can attain probably, let me say 30 degrees Celsius, and you're buying a sensor that the upper limit of that sensor is 20 degrees Celsius, definitely you can't get the appropriate information from such a sensor. So you need to get a sensor that the dynamic range covers and exceed the upper limit of what you want to measure. Then also the range is the difference between the minimum and the maximum. So you just want to know what is the difference between the minimum and maximum limit of that very sensor. Then we have the resolution, which is the minimum difference between two values. So what this one is saying is that for instance, some sensors can be measuring in a resolution of probably 22 units, some 11 units, some 0.5 units, and the lower the resolution, the more accurate your sensor will be. So that is one area that you can use resolution appropriately So you want to use a sensor that the resolution is very. So also we have the linearity, which is the variation of the output signal as a function of the input signal. We said for sensors, the transducer converts the physical quantity into a corresponding and proportional electrical output, probably voltage or current. So linearity is just the output signal in this case as a function of the input signal, which is the physical quantity in this case. Also, we have the bandwidth or the frequency. So, and that is the speed with which a sensor can provide a stream of readings. So, if you are used to, let me say, ultrasonic or probably camera before, if you have a camera that has a very high FPS, you can get like probably 60, 120 FPS, saying that you can get 60 frames, of images in 1 second, probably 120 frames of images in 1 second. That is the frequency, the speed at which, a sensor can provide a stream of readings. That is the frequency or the bandwidth. Also, there's the response time. So that is the time required for a change in input to cause a change in the output. So you would see, if you are buying sensors, some sensors, even when the physical quantity has changed, their own reading in terms of their electrical output wouldn't change, that quickly. So that is because their response time is very slow, and it's not good for some applications where you need a quick response time. So you want to pick a sensor that has a very high response time. So any little change in the output, there's always a corresponding change and proportional change in the output as well. So response time is equally very important. Then also sensitivity. It is a ratio of output change to input change. So just a ratio of the output change to input change. That's the sensitivity of a sensor. Then also you have the accuracy. Accuracy is just the difference between what is being measured and the actual reading. So if a sensor is telling you the temperature is 20 degrees Celsius and the actual is saying it is probably 22 or 25, that sensor is not very accurate. So you want to pick a sensor that the difference between the measured, what the sensor is measuring, and what is happening, is very minimal, so that you can have a high accuracy on your sensor. Also, there's what we call the repeatability of a sensor, which is the difference between repeated measures. So what you're saying is, if you have a sensor and you measure a certain quantity, probably temperature now or distance, and it says 20 centimeters, and you measure it again, it should tell you 20 centimeters. But if you measure it again and it's telling you it's 25, you measure it again another time, the same distance, it is telling you it's 28, then that sensor, is not very effective, because at every time you measure the same input, it's giving you different output, which is not appropriate. So that is about repeatability. So these are technical information about sensors that one has to look into before actually buying a sensor for any application. So the next thing we'll be looking at is sensors and control considerations. And we'll be looking at the kind of sensors that you find at the end effector of a robot arm, because we're talking about robot arm in this introduction to robotics extensively. So for the end effector, what are the kind of sensors that you would have there? Then we'll go on to talk about other sensors that you might find on your robot systems. So for the robot arm, which is the end effector in this case, the sensors that you commonly find at the end effector are the proximity sensor, the collision sensor, and the force sensors. Those are the common sensors that you find at the end effector of robot arms, because for your end effector, If, for instance, it is designed to grab something, then the force at which it is holding that thing. For instance, you want a robot arm to pick a glass cup or egg, for instance. You don't want it to apply so much force on the glass cup that it will actually shatter the glass cup, or or shatter the eggshell in this case. So you need to know what pressure can that eggshell sustain, what pressure in terms of force now that glass cup can handle. So at any time the gripper is holding the glass cup or is holding the eggshell, you need to be measuring the force, at which it is holding that the force on that very eggshell at that instance, so that you know when to release the grip or to hold the grip for a more firm grasp on it. So proximity sensors are one of the sensors you find, and we'll be just do some kind of overview on the proximity sensor in this case. So basically, the proximity sensors are presence indicators for your end effector. So you want to know if the end effector is actually grasping anything at that point in time. So they are typically presence indicator. So you want to know if your end effector is holding anything, and there are several types. So the common type you see is the optical proximity sensors that you see depending on the application, or you can use the true beam proximity sensor in this case. So there are several types depending on the application, but for any proximity sensor on the end effector, you just want to use it for a presence indicator, just to know if there's anything within the grasp of the end effector at that very instance. And one thing about sensors, on the end effectors of robot arm is that you don't want to put all the electronics of that sensor, in the end effector itself. You want to locate all the electronics of that sensor away from the end effector container, so to say, so that the electronics of that sensor will not be interfering with whatever you want to measure, in the end effector. So that's why you have here saying that most optical proximity sensors are available with an optical fiber end connection, so that sensors electronics will not necessarily be located on the end effector. So you don't want to locate all the electronics of that sensor, within the end effector, so that whatever you're measuring, the electronics of the sensor measuring that very quantity will not be an additional information that you'll be getting eventually. So that's about the proximity sensor. Also, we have the collision sensor. So for the collision sensor, you want to know if there's any possible collision for your robot arm in any direction. So what your collision sensor does for you is to detect a possible collision, with your robot in any direction. So I'm saying that a collision detection sensor can be a good end effector component to mitigate damage to the robot, itself, or any inserted part or workpiece where the part is being attached. So what collision sensor just does for you is to know how close your robot arm, either the end effector or even whatever it is holding at that time, how close it is to any other components within the environment. So if it is too close and collision is inevitable, then the robot might probably maybe stop its operation, or maybe track back to give more clearance, away from the intending collided obstacle, depending on how the program it is. um, how it is programmed to operate in such situations. So in most cases, it is to avoid the collision in most cases. So also there's the tactile feedback or force sensing. And I'm saying here that force sensing during grasping is important for the successful grasping of varying parts and complaint parts, and for reduction of part deformation. Just like I've said earlier, when it comes to grasping, you know, you need to grasp with the appropriate force so that you don't deform what you are holding. You know, the force that you use in holding an egg is not the same force you use in grasping a wood, for instance, because you know that if you apply the same force that you use in grasping a wood to an egg, you will deform the eggshell. So the same way too, when you have a robot arm that grabs anything, you need to know what force can that entity sustain, and you don't want the robot arm to exert any force more than that from the gripper to that entity so that it won't deform it. So that's where your force sensing comes in. So what will happen is that whenever the force is going too high and can end up in deformation, then in such scenarios, the grasping control will be released so that the force can be reduced and prevent deformation. So force sensors that can be used can be a piezoelectric force sensor. They are available readily, and they measure dynamic loads very appropriately, you know. So, or your piezo resistor force sensors can also be used for tactile force sensing using the principle that resistance of silicon implanted piezo resistors will increase when the resistor flex under any applied force. So the sensors that you might see for force sensing can be your piezo resistor force sensor, can be your piezoelectric force sensor. So it depends on what you're using in that case. Then there is also what we call the acceleration control for payload limits, which is another important control aspect for force during acceleration. So the acceleration control actually measures the acceleration of the joint motion for your gripper, because at the end of the day, how fast your joint for your gripper is moving will determine the force that will be applied eventually. So I said another important control aspect is the force caused during acceleration, particularly of the joint. So in most instances, the acceleration of the joint has to be measured, has to be known, so that it does not over accelerate to, cause a lot of, or to exert a lot of force on the payload that is being grasped by the uh, gripper in this case. So other sensors and applications that you find on your robot arms are the rotary and linear incremental encoders, because you know that robots, particular robot arm, deals with joints, and the kind of joints that we have are either a linear joint or a rotary joint. So aside the sensors that you find on the end effector that we have discussed earlier, other sensors will be on the joint in this case, and the joint can either be a linear joint or a rotary joint. So the sensors that you now find on the joint of your robot will either be a rotary or a linear incremental encoders. That is the kind of sensors that you might find generally on the joints of your robot arm. So I said incremental encoders are the most common feedback devices for robotic systems, particularly on the joints anyway. So what they do is they output digital pulses, you know, at intervals to tell you what is the position of that joint. So if you already have a control that this joint should be on this position, probably uh, 60 degrees in terms of your servo motor or your any motor that you have used to get the joints at which your robot arm should be at a certain coordinate, then you need an encoder to be able to measure if that position is appropriate or not. And when that position is not appropriate, there should be a way that you need to correct based on the programming on the controller of that robot arm. So that adjustment can be made so that the robot arm can get to the coordinates that is being expected. So you can see here in figure 3.1 a typical encoder, and you have your light source, your disk, and that disk has a lot of slots. So, and you have the photosensor pickup at the other end. So when the light goes through, that means there's no obstruction of that uh, light ray from the disk. And when the photosensor cannot pick up the light ray, then it counts that a very instant as a pulse. And since it's a rotary information in this case, so it keeps counting the pulse, just like you have an encoder on a motor. So based on the number of ticks that encoder goes, you can determine the revolution that motor has gone, and based on that you can calculate the angle if it's a angle based motor. Now you can calculate the angle, based on your programming, your controller, to know if that joint is at the required position that you intended it to be. So another example of the incremental encoder that you find on your robot arm is the tachometer. So a tachometer is an incremental encoder with a single photo detector. So that is a tachometer, and what tachometer does is to measure. So what it does is to measure the rotational speed of your DC motor shaft. However, for a tachometer, you can't use a tachometer to determine the direction of which your shaft is going. If it's going forward or backward, you cannot know because it has only one photo detector. So for you to know the direction, if it's going forward or backward, then you can't use a tachometer. You need to use an encoder that has at least two photo detector, one for forward detection and one for backward detection. So with that, you can know the direction. But for a tachometer, you can only know the rotational speed of the shaft of your motor. You can't tell the direction because it has only one photo. So another type of your incremental encoder is your quadrature encoders. So for your quadrature encoders, there are two channels which uses two photo detectors to sense both position and direction. So that's the advantage of that over the tachometer, because it can actually sense, the position and direction in this case, unlike the tachometer that cannot, do such sensing. So here is just the figure showing the clockwise motion and the counterclockwise motion of your quadrature encoders, just to know if it is going forward or backward and what position it is based on how it is changing from the 90 degree that is being used to track the rotation in this case. Also, we have absolute encoders. So absolute encoders can read the position So absolute encoder can be used to read a position, because in some instances you might need to read the position of your motor immediately your robot system starts up. So in that case, you need an absolute encoder to tell you at startup what is the position of your motor, so that that position can be used as the initial input. Then whatever command you want to give will just be uh, the difference to where you want the position to actually be, since you already know the initial position using your absolute encoder in this case. So there are instances whereby you need to know at every startup of your robot system, you need to know the position of your motors on the joints. So you need an absolute encoder to measure the position in such case. So the absolute encoder is equally similar to the incremental encoder, except that the disk that is being used in the absolute encoder has multiple concentric code tracks, and is separated by a separated photo detector is used for each code track, so that the position can be measured more appropriately compared to what you have in the quadrature encoder. Also, there's the use of vision systems in robotic system. Now, this is where the issue of machine vision comes in. So machine vision is a way by which a certain machine can make decision based on information extracted from images. So for instance, if you have uh, a robot arm that you want to use in sorting, for instance, and let's say you have a bottling line whereby you have used machine vision to measure the level of content in that bottle. So you have already trained your system to know the appropriate level in each bottle, and any bottle that is not at the appropriate level, you want that bottle to be rejected, so that only bottles that are filled appropriately can continue on the production line. So a robot arm can be used as a sorting agent in this case. So for that robot arm to know when to probably remove a certain bottle from the line, then a vision system must have been used, which is trained, before being deployed, to recognize the normal level in the bottles. And any bottle that does not attain that level, then the robot arm now gets activated to reject or probably to remove that bottle from that line. So that is what vision system does. Also in assembly, particularly in automobile assembly, vision systems are very important, so that the robot arm can properly assemble the vehicle parts, because without vision system there's no way such can be achieved with robot arms. So vision systems are equally very important, when it comes to uh, robotic systems, particularly cameras. And these are cameras that are high-end cameras majorly. These are cameras that can measure distance, cameras that can, give you probably over 3, 4, 500 frames, per second, so that the precision is, very, very accurate.